Imagine two manufacturing plants side by side. Plant A produces this flawless piece of high-end machinery every 60 seconds, just running like a Swiss watch.
Right.
But Plant B, building the exact same product, is drowning in $1 million recall. They've got a warehouse just full of scrapped parts and, frantic executives looking for someone to blame.
Oh, yeah, the classic panic mode.
Exactly. And the difference between these two operations, it isn't the robotics they bought, and it isn't the talent of the engineers on the floor. It all comes down to a deeply structured, heavily mathematical architecture.
Yeah, it's an architecture that treats perfection not as this, lucky outcome, but as an inevitable mathematical byproduct. Today, we're digging into the frameworks these top-tier organizations use to achieve near-perfect continuous improvement. We're synthesizing decades of operations research, lean manufacturing principles, and statistical process control for you today.
Okay, let's unpack this, because getting to that level of perfection, it requires a fundamental shift in how an organization even defines success. I mean, you can't just walk onto a factory floor, point at the assembly line, and just mandate that everyone works faster and makes fewer mistakes.
No, definitely not. You need a philosophical blueprint first.
Right. And the sources we're looking at for this deep dive, they point to a specific hierarchy called the sand cone model.
Oh, the sand cone model. It completely flips conventional corporate strategy on its head.
How so?
Well, picture pouring sand onto a table. It naturally forms this wide, stable base, right? And it tapers up to a peak. You physically cannot build the top of the cone without the base expanding first.
Okay, yeah, the sand just falls away.
Exactly. So in this model, the foundation, the widest and most non-negotiable layer, is quality. Once you have absolute quality, you can stack dependability on top of it.
Right.
Then and only then do you build speed. Above speed sits flexibility. And finally, sitting at the very peak, like the ultimate result of the other four layers, is cost.
I really love this visual. Think of it like learning to play the guitar. You can't start by trying to shred some frantic, improvised solo.
Right, which represents your speed and flexibility layer.
Exactly. If you do that, it's just going to sound like chaotic noise. You have to learn how to hit the right notes first, the quality. Then you have to be able to play them correctly every single time you pick up the instrument, which is dependability. Only then can you actually start playing fast.
That's a perfect analogy.
But I have to push back here, because this entirely contradicts how a lot of businesses actually operate out in the real world. You see companies all the time saying, our competitive advantage is going to be aggressive pricing, and they just immediately start hacking away at the budget. I mean, why can't a company just start at the top of the cone?
Because if you rush to cut costs first, the entire sand cone collapses underneath you. It's a mathematical certainty.
Really?
A certainty.
Absolutely. Quality isn't just an added luxury feature, it is an essential structural requirement. Now, investing in that foundation initially, it drives your expenses up. Right, the CFO is looking at the balance sheet and sweating.
Oh, for sure.
Yeah.
You're paying heavily for preventive maintenance, exhaustive worker education, premium materials. These are categorized as prevention and appraisal costs.
So the short-term financial pain is very real.
It is. But the financial pain of investing in quality is absolutely nothing compared to the bleeding caused by ignoring it. When you bypass quality to save $1 today, you inevitably trigger massive internal and external failure costs later.
And internal failures, that means you're throwing away scrap material, right? Or like paying workers to rework a defective part before it even leaves the building.
Yeah, exactly. But the external failure costs are the truly catastrophic ones. That happens when the defective product actually reaches your customer.
Oh, wow.
Suddenly, you are hemorrhaging money on warranty claims, massive logistical returns, lawsuits, and just the total destruction of your brand reputation. Not investing in quality is, ironically, the most expensive choice an organization can make.
So, assuming leadership actually internalizes this, like they accept that quality is the foundation, how does that philosophical shift translate into physical reality? How do they structure the floor to actually pull it off?
Well, the blueprint for this is known as the House of Lean, or sometimes the House of Toyota.
Oh.
And it relies heavily on just-in-time manufacturing, or JIT.
Oh, JIT. We know the basics of JIT, producing only what is needed, driven by the heartbeat of customer demand, which is called takt time.
Yep, it's takt time.
But looking at these sources, operating a true pull system without massive safety buffers of inventory, it seems incredibly fragile to me. You're operating entirely without a safety net. If a single scratched part comes down the line, doesn't the whole day's production just grind to a halt?
It does, which is exactly why just-in-time cannot exist in a vacuum. It absolutely relies on the second core pillar of the house of lean, which is Jidoka.
Jidoka.
Yeah. It translates roughly to automation with a human touch, and it focuses on doing things right the very first time. It utilizes physical mistake-proofing mechanisms known as poka-yoke.
Oh, like an asymmetrical electrical plug that physically cannot be inserted backward.
Exactly. But the most radical component of Jidoka is the mandate to completely stop the production line the exact moment a defect is detected.
See, this is where I struggle with the logic. You have a factory burning thousands of dollars a minute in operating costs, and an operator finds a minor scratch on a panel. Stopping the entire line for that seems like a massive overreaction that just totally destroys your just-in-time flow. I mean, you're killing productivity over a scratch.
I get why it looks that way, but what's fascinating here is that our normal definition of productivity is often deeply flawed. True flow is not about moving fast. It's about moving without creating waste.
Okay.
If you refuse to stop the line when you detect that scratch, you're effectively using your highly efficient just-in-time system to mass-produce garbage at record speeds.
Wow. Yeah, that makes sense.
Right. By stopping the line, investigating the root cause of that scratch, and implementing a permanent fix right then and there, you are preventing 10,000 future defective products from being built. You absorb a minor delay today to guarantee flawless flow tomorrow.
Oh, I see. You're basically cutting off those external failure costs before they can even materialize.
Exactly.
And the metric they use to track if this delicate balance is actually functioning is called OEE, right? Overall equipment effectiveness.
Yes, OEE is crucial. Instead of just looking at total output, OEE forces management to confront the 6 big losses.
What are those?
They track the loss of availability, like unexpected machine breakdowns or sluggish setup times. They track the loss of performance, meaning a machine is, idling or running below optimal speed due to wear. And they track the loss of quality, which is the scrap and rework we just talked about.
So those OEE metrics basically remove all the hiding places for inefficiency.
They really do. But here's the thing. A perfectly designed house of lean with flawless OEE tracking is completely useless without the people operating inside it.
Right?
These continuous improvement systems absolutely require deeply empowered human beings. A system this tightly wound cannot function if workers are just mindlessly turning wrenches and waiting for a manager to tell them what to do.
Empowerment gets thrown around a lot as a corporate buzzword, usually meaning like casual Fridays or a suggestion box in the break room.
Yeah, pizza party.
Right. But the sources outline this as a strict mechanical necessity. They break it down into job enlargement and job enrichment.
Let's talk about the difference there.
Okay, so enlargement is horizontal. You give workers more sequential tasks to build a broader skill set and reduce fatigue. So instead of just tightening one specific bolt all day, they assemble the entire subcomponent.
Exactly. Enlargement builds a flexible workforce. But job enrichment is where the real power lies. Enrichment is vertical. It transfers actual autonomy and decision-making authority down to the operator,
making them the boss of their own process.
Yeah. The philosophy is simple. The person spending 8 hours a day interacting with a specific machine understands its nuances far better than an executive in a boardroom. They must be given the authority to optimize how that job is performed.
But you can't just hand someone authority without structure, right? I mean, the framework outlines a concept called worker self-control. If you genuinely want an employee to own the quality of their output, they require 3 non-negotiable things.
Right, 3 things.
First, they need total clarity on what they are supposed to accomplish. Second, they need real-time knowledge of their actual performance against those goals. And third, they need the physical tools and the authority to actually regulate their own performance.
And if we connect this to the bigger picture, this represents a massive shift in corporate accountability. Think about it. If leadership fails to provide a standardized process, or ignores giving real-time feedback, or restricts access to the tools needed for correction,
then they can't blame the worker.
Exactly. They logically cannot hold the floor worker responsible for a defect. In a system lacking worker self-control, the failure belongs entirely to management.
That brings up a massive translation issue, though. We said the first requirement for worker self-control is knowing exactly what to accomplish. But how does the floor worker actually know what the customer values?
Oh, that's a great question.
Because the voice of the customer is usually incredibly subjective, Let's say you're manufacturing transit doors. A city planner tells your sales team, We need doors where it's really easy to remove graffiti.
Right, a very common request.
Sure, it's a perfectly valid customer desire. But a machinist can't program a laser cutter based on easy to clean.
Bridging that gap between subjective desire and objective manufacturing, that is one of the hardest challenges in operations. To solve it, companies deploy a matrix called Quality Function Deployment, or QFD. Specifically, they build a house of quality.
How's it quality? Okay.
Yeah, this matrix takes that subjective voice of the customer, that desire for easy graffiti removal, and mathematically translates it into strict target engineering values.
So it takes easy to clean and assigns it a specific requirement, like polycarbonate coating thickness must be exactly 1.2 millimeters.
Precisely.
Oh,
But it goes further by mapping out the engineering trade-offs. What if that same customer also demands the door be extremely lightweight for energy efficiency? Increasing the polycarbonate thickness makes it heavier, right? Putting those two desires in direct conflict.
so the QFD matrix forces engineers to balance those competing requirements mathematically.
Exactly. Ensuring that the final specifications given to the empowered workers are perfectly calibrated to deliver exactly what the market actually values.
Okay, so the workers have their exact engineering targets. They're fully empowered with self-control. The Jidoka systems are in place. But entropy always wins, right? Things are going to break. A defect is inevitably going to slip through.
It happened.
When that happens in a true continuous improvement culture, they don't panic and they don't just guess at a solution. They trigger rigid, scientific problem-solving frameworks. And the most famous of these is Six Sigma.
Yeah, Six Sigma sets a standard of perfection that almost sounds impossible. The goal is to compress process variations so tightly that you experience no more than 3.4 defects per million opportunities.
3.4 per million, that's wild.
Right. At that level, a defect is no longer a routine annoyance. It is a profound statistical anomaly.
Here's where it gets really interesting, because to achieve that 3.4 defects per million, organizations rely on a methodology called DMAI. Define, measure, analyze, improve, and control.
DMAI is incredibly powerful.
It ruthlessly prioritizes fact-based decisions over gut instincts. You can think of DMAI exactly like how a highly skilled doctor treats a patient.
Oh, the diagnostic parallel is very strong there.
Yeah, like when you go to the doctor feeling terrible, they don't just hand you a scalpel and say, let's try some surgery. First, they ask you to define your symptoms. Where's the pain? When did it start? That's the D. Right? Then they measure your vitals. They get objective data on your blood pressure and heart rate. That's the M. Next, they analyze those measurements alongside your lab results to isolate the actual root cause of the illness. That's the A. Only after all of that data is processed do they actually improve the situation by prescribing a medication.
And this is exactly where most corporate problem solving fails. Managers love jumping straight to the improve phase because, well, it feels like action.
Yeah, they want to look busy.
Exactly. They start tweaking machines or changing protocols before they've properly measured or analyzed the root cause. It is the literal equivalent of a surgeon operating blindfolded.
Totally. And the most critical step is the final one, control. The doctor schedules a follow-up appointment in 2 weeks to ensure the medication is actually working and that your vitals haven't slipped back into the danger zone. You have to actively control the process to lock in the gains you just made.
That concept of locking in the gains is the driving force behind another iterative framework they use, the PDCA cycle. Plan, do check, act. It basically functions like the scientific method for the factory floor. You plan by identifying a specific problem. You do by testing a potential solution on a small scale. You check by meticulously studying the data from that test. And, if the data confirms success, you act by officially standardizing the solution across the entire operation.
So both DMASC and PDCA are basically relentless engines designed to push that sand cone higher.
Exactly.
But let's talk about the reality of the floor. You've run your DMAIS project. You've standardized the solution using PDCO. How do you prevent human nature from taking over? Like if you walk away for a month, how do you ensure the process doesn't just quietly slide right back into the old chaotic way of doing things?
That's the real challenge. To prevent that backslide, you rely on environmental design and rigorous statistical monitoring. The physical layer is work area design, utilizing visual management.
Meaning configuring the workspace so that abnormalities are instantly obvious.
Exactly. You implement shadow boards where tools have their exact shapes painted on the pegboard. If a wrench is missing, anyone walking by knows it immediately. You arrange equipment into continuous flow cells rather than isolated islands, minimizing unnecessary motion and making the flow of materials completely transparent.
Okay, so that covers the physical environment, but you also mentioned statistical monitoring. The mathematical tool used to hold the line is statistical process control, or SPC, and this requires a really deep understanding of variation.
It does.
Every single process in the universe has variation. If you cut a piece of steel to exactly 1 inch and you do it 10,000 times, there will always be microscopic differences. But SPC draws a massive line between common cause variation and special cause variation.
Yeah, think of variation like your daily commute to work. Let's say it usually takes you 70 minutes, but some days it takes 28 and some days it takes 33. That fluctuation is caused by normal traffic patterns, weather, traffic lights. That is common cause variation.
Just background noise.
Right. It's the inherent background noise of the system. It's random, but it fluctuates within a predictable, stable range. Special cause variation, however, is a massive, unpredictable disruption.
Like getting a flat tire on the highway or a bridge being unexpectedly closed.
Exactly. A flat tire isn't part of the natural system. It means an assignable event occurred. In manufacturing, a special cause might be a machine bearing suddenly wearing out, or a new untrained operator accidentally changing a setting. SBC is entirely designed to filter out the common cause noise so you can instantly detect when a special cause has entered your system.
And the primary tools for this detection are control charts. We track the data over time, but to actually read these charts, we have to grasp a vital distinction. We have specification limits and we have control limits. They sound super similar, but confusing them is a recipe for disaster.
Oh, absolutely. Specification limits, the lower and upper spec limits, are dictated by the market. They represent the voice of the customer. They tell you the absolute boundaries of what the customer will accept before they consider the product effective. Control limits, on the other hand, represent the voice of the process. They are derived from the actual statistical behavior of your specific machines. They show you what your equipment is naturally capable of doing, regardless of what the customer wants.
So we map the voice of the process out visually. Let's look at the X-bar chart, which tracks the average of your samples over time to monitor the central tendency of the process. The magic here isn't just staring at the chart waiting for a data point to wildly cross the control limit line.
Right, because by the time that happens, you've probably already produced a defect.
Exactly. The true power of SBC is finding hidden patterns before the failure occurs.
And the sources outline specific mathematical tests, like Nelson's tests for special causes, to decode those patterns. Let's say you're looking at your X-bar chart, and all your data points are comfortably inside your acceptable control limits. Everything looks fine at a glance. But if you apply Nelson's rules and notice that 6 consecutive points are steadily increasing, forming a subtle upward staircase, that is a massive red flag.
Even though none of those 6 points have crossed the line into defect territory yet.
Correct. The mathematical probability of 6 random common cause points perfectly ascending in a row is astronomically low. That specific trend indicates that a special cause is actively dragging your process out of alignment.
Like a cutting tool slowly dulling with each pass.
Exactly. And by identifying that trend, the operator can stop the machine and replace the tool while the product is still perfectly within specification. You've effectively neutralized the defect before it even existed.
Wow. So what does this all mean for you listening? If you're managing a team or overseeing a complex system right now, this is where the math gets genuinely terrifying. We're tracking the voice of the process and checking it against the voice of the customer. Can a process be completely mathematically stable, like perfectly in control on its X-bar chart, showing 0 special cause trends, but still be an absolute catastrophic failure?
That's the million-dollar question, isn't it? And the answer highlights the most dangerous blind spot in manufacturing. Yes, absolutely. This is the critical distinction between process control and process capability. A process can be perfectly in control. It has a flat trend line, it's highly predictable, and it only exhibits normal background noise. But it can be entirely incapable.
Meaning your highly predictable, perfectly stable machine is consistently and reliably producing total garbage.
Yes. Because its natural variation, the voice of the process, is wider than the strict boundaries demanded by the voice of the customer. To determine if this is happening, engineers calculate capability indices, specifically CP and CPK.
Okay, let's break this down.
The TP metric measures the total width of your process spread against the specification limits. It basically asks, is the total variation of our machine narrow enough to physically fit inside the customer's acceptable window?
But knowing the spread isn't enough. Think of a dartboard. Having a fantastic SEEP score means you have thrown a super tight, highly clustered group of darts.
Right.
The variation is incredibly low. But CP doesn't care where those darts actually landed. You could have a perfectly tight cluster that's hitting the drywall 3 feet to the left of the actual dartboard.
Which is exactly why CP is meaningless without CPK. CPK measures whether that tight cluster of variation is actually centered directly on your target. You must have both.
So narrow and centered.
Your process must be narrow enough to be capable, and it must be centered enough to be acceptable. The statistical voice of the process must comfortably nestle entirely inside the voice of the customer.
And when it does, that is how you hit the 3.4 defects per million. Well, we have covered some serious operational ground today for this deep dive.
We really have.
We started by laying that unshakable foundation of quality at the bottom of the sand cone model. We used that philosophical shift to construct the physical house of lean, utilizing just-in-time flow protected by the vital mistake-proofing of Jidoka. We explored the absolute necessity of empowering workers with the tools for self-control, ensuring they're guided by objective targets translated through quality function deployment. And when the inevitable breakdown occurs, we learn how to diagnose the root cause using DMAIC, ultimately locking in our gains with the rigid statistical monitoring of control charts and capability indices. Producing flawless products year after year, it isn't luck and it isn't magic. It is this exact, deliberate mathematical architecture.
It is an incredibly beautiful, deeply human system of constant refinement. But it does leave us with a final, somewhat unsettling thought for you to mull over.
Oh, what's that?
Well, throughout this entire deep dive, we've focused heavily on the human element, right? Worker empowerment, autonomous decision-making, physical visual management on the factory floor.
Right, empowering the people.
But as we sprint toward emerging technologies, hyper-advanced artificial intelligence, predictive data analytics, and autonomous robotic solutions, we have to wonder, will the voice of the process eventually be monitored and corrected entirely by machines?
Oh, wow.
Will a central AI recognize a subtle drift on next bar chart and adjust the microscopic calibration of a robot arm in milliseconds, completely bypassing the human worker? Will the continuous improvement loop eventually close itself? It's something for you to explore as the future of manufacturing unfolds.